Today, we are going to talk about electromagnetic induction. Our learning target for this lesson is I can describe the process of electromagnetic induction and its importance to our modern world. Our essential questions are, what is electromagnetic induction? How do you generate electricity using magnets? How does a generator work? And what is the difference between AC and DC generators? Let's start out by talking about what electromagnetic induction is. Well, we know that an electric current makes a magnetic field. We saw this in practice when we were doing Orsted's demo. We made that wire loop and connected it to a circuit, and the wire loop affected the compass. We've also seen this in our electromagnets and our solenoids that we've made. All sorts of times we've seen that an electric current can make a magnetic field. Well, a magnetic field can be used to make an electric current. So the opposite of what we've been doing, we can do that as well and use a magnetic field to make an electric current. So here's our definition. Electromagnetic induction is the process of generating a current by moving an electrical conductor in a magnetic field. So this comes from Faraday's law. Faraday stated that a voltage is induced in a conductor by a changing magnetic field. Okay, let's break down what that means. A voltage is what will lead to a current if the conductor is connected to a circuit. The conductor is anything that conducts electricity, so some kind of metal. And a changing magnetic field. All that means is that the magnetic field is in motion compared to the conductor. So that's what we're saying. So when we look at this, diagram that we have here, when a magnet is in a solenoid that is a part of a circuit, if either the magnet or the wire move, a current will be produced. So what this is saying is if we take this magnet here and we push it through this solenoid, then that will create an electric current. The same thing if we had a magnet just sitting here and we pushed this solenoid over the magnet, it would also create an electric current. As long as the magnet and solenoid are moving relative to one another, then that is going to mean that an electric current will be produced. So let's talk about generators. Most electrical energy that we use is produced in power plants using generators. A generator is a device that converts mechanical energy by rotating a coil of wire in a magnetic field. So, the motion of the coil in the magnetic field produces an electric current. This is what we just got done talking about with the electromagnetic induction. And so we have a device now that does this. There are two types of generators, AC and DC, or alternating current and direct current. We talked about alternating and direct current in our electricity unit, and so now we're going to talk about how those things are made. So let's talk about how an AC generator works first. An AC generator produces alternating current in which the current changes direction constantly. So a wire loop right here is placed between two permanent magnets, North Pole, South Pole. As the loop rotates, the magnetic field induces an electric current in the wire. So we have the wire loop rotating here, and because you have the motion of a coil or loop of wire in a magnetic field, that induces a current. Now, as this loop rotates, it is inside of these two what are called slip rings, which are just metallic conductive rings that the wire loop touches the metal. So those are now part of the circuit. And so those rings then connect to a circuit where the current goes. And so you induce your electric current in your loop here, and it travels into the rings and out into your circuit as AC voltage. It's literally just an electric motor in reverse. Instead of putting electricity in and creating mechanical movement, we are putting mechanical movement in and producing electricity. So let's talk about a DC generator now. It is very, very similar to an AC generator. It produces direct current, which should make sense as opposed to an AC generator. As the loop rotates here, an alternating current is induced because you have the north and south pole here. The current being produced is going to change directions because the wire loop is constantly changing directions. However, at the end, this is kind of hard to see in this diagram, but this right here is a commutator, which we see is two pieces of C-shaped metal. Okay, so they don't connect. So that's the important part. They do not connect. So as the wire loop and the generator rotates, the direction of the circuit is constantly changing. So we know that it's just physically moving, and so the direction is changing. Since the current and the circuit are constantly changing direction at the same time, they cancel each other out. And as a result, you get a current moving in one direction. So as this rotates, the current being produced is alternating current because it is changing the magnetic field. It's changing directions in the magnetic field constantly. But as it moves, every time it changes direction, these commutators change which part of the circuit they are touching, and so the current that comes out is only moving in a single direction.